Welcome to the first video in this neural network series. Today, we will learn the math behind neural networks. However, before we jump into that, we need to review a couple of concepts. First, matrix multiplication. Matrices and their higher dimensional analog, tensors, are a common way to represent data in arrays. This is often the case with the weights and biases in a neural network. And using matrix multiplication, we can have the model make predictions. So, if we want to multiply two matrices together, we must ensure that their shapes match. That is, the number of columns of the first matrix must be equal to the number of rows of the second matrix. The resulting matrix will also have as many rows as the first matrix and columns as the second matrix. Now, to see why, let us take this example and manually multiply these two matrices. We first have to multiply the first column of the second matrix with each row of the first matrix and use the results to fill out the first column of the resulting matrix. We then repeat this with the remaining columns of the second matrix to get the result of multiplying the two matrices. The second concept we need to go over is the chain rule. Now, differentiation is the process of finding the derivative of a function. And physically, the derivative can be understood as the slope of a function, and it tells us how fast the function is changing with respect to an independent variable. For example, here, the function is changing quickly at this point and has a large derivative and slope, while here it is changing slowly and has a small derivative. Derivatives of a function are always calculated with respect to an independent variable. However, when we have functions which vary with respect to other functions of the independent variable, we must use the chain rule to find its derivative. For example, here f is a function of g, which is in turn a function of x. So to find its derivative, we need to find how f varies with respect to g and how the function g varies with respect to x. Now that we've gotten the basics down, let's move on to discussing neural networks. A canonical neural network you may have seen before would look like this, with neurons and connections between them. Here, the first layer where the data is input to the model is called the input layer, and the last layer where the model generates its outputs is called the output layer. All intermediate layers are called hidden layers. The model works by taking inputs to each layer, multiplying them by their corresponding weights, represented by these colored arrows, adding an optional bias term, and passing the result or pre-activated output onto the next layer. To understand this math, let's simplify this down to a one neuron input and output model. Given an input x in this model, the output, if the weight of this edge was w and there was a bias term b, would be wx plus b. Now, this looks like the equation of a line. In fact, if this model is allowed to train and optimize the loss function, that is, minimize the error between its predictions and the expected output, we would arrive at a linear regression solution. But unfortunately, most relationships in real life are hardly linear, and we need to introduce some non-linearities into our model. We do this by using activation functions. These functions take these pre-activated outputs of each layer, pass them through a nonlinear function, and return the activated output. Some common functions that are used for these are ReLU, sigmoid, tanh, and softmax. This process of multiplying the layer inputs with the weights, adding a bias term, and applying an activation function to get the layer output is repeated in every layer of the neural network to get the model's output to a given set of inputs. This process is called the forward pass of the neural network. The model prediction at the end is then compared to the expected output, and the error is calculated using a loss function. Now, there are different kinds of loss functions for different purposes. Two of the most common types of tasks neural networks are used for are regression and classification. Regression involves finding a function that maps the input parameters to the output parameters. For example, linear regression, where we try to fit a line to a set of data. In these tasks, the mean squared error is a commonly used loss function. The other task, classification, involves classifying an object with certain input parameters into two or more classes. For these tasks, the two most common loss functions are the binary cross-entropy loss and the categorical cross-entropy loss. Now, so far we have explored the predictive capabilities of a neural network. That is, given an input, what would the model predict to be the output? However, what if the prediction is wrong? And this often happens when the model is not yet trained, when the model has random weights and biases instantiated. That is when the error that is calculated by the loss function must be propagated through the model, and the weights and biases need to be adjusted to improve the prediction. And this is where backpropagation comes in. The core idea behind backpropagation is gradient descent to minimize the loss function. This is an iterative algorithm that attempts to find the combination of weights and biases that minimizes the model's error on the training data. That's a lot of words. Let's just go back to a simple one input, one output example and work through it. The only parameter in this model is the weight W. Suppose the prediction of the model is very close to the expected output. Then the update to the weight is small to improve the model accuracy. Conversely, if the prediction is far off, the update needs to be more drastic. We can make these conclusions because the output depends solely on W. If there are more weights and biases in the network, then the updates to each weight are determined by the effect that that weight has on the model output. To calculate this quantity, we need to find the derivative of the model output with respect to that particular weight. And this is where the chain rule comes in. Let's use the chain rule in the one input, one output case from before. We'll include an activation function f in this example as well. Assuming that the pre-activated output is z, the model output is O, the expected value is E, and the loss function we are using is the mean squared error, the loss will be O minus E squared. We want to find the derivative of the loss function with respect to the weight W. Using the chain rule, we can calculate this as del loss over del O times del O over del Z times del Z over del W. Because the loss function depends on the model output, which in turn depends on the pre-activated output because of the activation function, and the pre-activated output depends on the weight W. To fully understand backpropagation, let's consider this extended case. Note that the lowercase letters in the hidden layer represent the pre-activated output, while the uppercase letters represent the activated output. The effect each weight has can be calculated as follows. We simply look at each path from the output node to each inner node and find the derivatives up to that point. If we observe these terms carefully now, we notice that the first three terms in the product were kind of calculated in the last layer of the neural network. The only difference is that these terms are derivatives with respect to A and B, not W3 or W4. This is crucial because this means that we can reuse computations of these red terms from previous layers while calculating derivatives. In fact, this is where the name backpropagation comes from. The gradients calculated in one layer are propagated backwards to previous layers, drastically reducing the number of computations required. Another important fact to notice here is that the effects of each weight and the updated derivatives to propagate to the previous layer can also be calculated using matrices as follows. This is how we will implement the backward pass in the code. After this backward pass is complete through all the layers of the model, the weights are updated by subtracting the update matrix. Oftentimes, the update matrix is also scaled by a value called alpha or learning rate to ensure that the optimization algorithm does not jump over the minimum. One final thing we need to keep in mind is that training the model on one example at a time is called stochastic gradient descent, and it can be ineffective in some cases because of extreme or outlier data points. So, the common remedy is to train in batches. Each batch contains multiple input data points that are processed together. For example, a common batch size is 32, which means that the neural network makes predictions for 32 examples at a time and uses the aggregated error from all 32 examples to update its weights. This reduces the chance that a few outliers drastically alter the program weights, and since we're using matrix multiplication, can be a little bit more efficient. We will implement the neural network with a batch size parameter, which should clarify this concept. And that's all the math involved in neural networks. If any parts are unclear to you, be sure to rewatch them either now or after walking through the implementation with me. Thanks for watching, and I'll see you in the next one, where we begin implementing the neural network library.